can you see my screen? Everything is okay?
Yes, we can.
So let me change my point options. Okay, so I think I'm ready. So let me get started. Okay, so again, hi everyone. I'm very honored to make a presentation today for DMI talk by IEEE MTT. So my topic today is electronics in extreme frequencies, and let me start today's talk with a couple of slides, pictures I prepared. So first picture, what is this? So some of you may wonder what it is, and some of you may have guessed. Yes, that is our very first transistor in the world, invented in 1947 December, right? Yeah, so last year, the world celebrated 75th anniversary of the transistor, and it is already 75 years since the transistor was invented. So who invented this transistor? So it was three gentlemen shown here at Bell Lab, USA. So Shockley and Breton and Bardeen, they invented this transistor, and they awarded 1956 Nobel Prize for the invention of transistor. So for that 75 years of history, the transistor has gone through a great evolution, and the performance of the transistors has greatly improved owing to the innovations in both material and structure. And one of the key performance is operation speed. So let me bring you to next slide, which shows the trend of operation speed of silicon germanium HBT. So what is silicon germanium HBT? So be patient, I will get back to that point several slides later. So this is one type of transistor. So what it shows is operation speed over time. And like 30 years ago, it was below 100 gigahertz, but now the operation speed is around 700 gigahertz. And with that operation frequency, you can design circuits operating well beyond 100 gigahertz or very high frequency or extreme frequency I'm mentioning today. So with this background, let me get to the main point of my presentation today. So this is outline of my talk today, and there are 4 topics. So first, I will show you some frequency spectrum, especially for those frequency band not very explored. And then I will be talking about transistors operating at extreme frequencies and circuits operating at extreme frequencies. Then I will show some application example. Okay, so let me start with that frequency spectrum. So what it shows is kind of various different frequency bands, electromagnetic spectrum over frequency axis. And for lower frequency part, we have like radio frequency or microwave, and those frequencies are covered by electronics traditionally. And upper frequency part about visible light, X-ray or gamma ray, those frequency band has been traditionally covered with optics, right? And located in between this and that frequency band is about 0.1 to 10 terahertz. You know what is terahertz? 1 terahertz is 1,000 gigahertz or 1 million megahertz. So that's very high frequency, and that frequency range has not been developed, much developed compared to this neighboring frequency band. The main reason being the lack of device that properly operate or properly process signals at that high frequency. And for that reason, that frequency is called a terahertz gap, right? But there are many interesting applications for that frequency range, very high frequency range. So there have been many efforts to develop this very high frequency band. So there have been two approaches to develop this frequency band, or say to fill the terahertz gap. One approach is from downward with electronics, upward from electronics. The other approach is downward approach from optics. And today I'll be mostly talking about the approaches from electronics, which is usually transistor based, and it benefits from its compact size and low cost and low power consumption. Okay? So what are the opportunities for terahertz band? So terahertz band is very high frequency, so that frequency band can provide a very wide frequency band, which is very good for broadband communication applications. And high frequency means short wavelength. So short wavelength is good for high resolution imaging or high resolution radar. Also, because of the short wavelength, you can realize component size very small. So that is another advantage for using high frequency, because that is short wavelength. So with those background at hand, I will bring you to many different types of transistor operating at that very high frequency or extreme frequencies. All right. So there are many different types of transistors, and we can group those transistors into two groups based on the materials they are based on. First group is silicon-based transistors, and the second group is 3-5 transistors or compound semiconductor transistors. Or based on structure of transistors, you can divide transistors into another set of groups. One FET, which is a field effect transistor, and another is a bipolar transistor. And for each category, we have many different types of transistors available these days. So for example, MOSFET is silicon-based transistors with FET structure. And for silicon-based bipolar, we have options like silicon BJT. BJT means a bipolar junction transistor, or silicon germanium HBT. HBT is heterojunction bipolar transistor. Or for 3-5 transistors, we have JFET, junction FET, or MISFET, metal insulator semiconductor FET, HEMT, and MESFET. They are 3-5 transistors with FET structure. And also we have 3-5 or compound HBTs, which is 3-5 transistors with bipolar structure. So when we talk about a microwave transistor or transistors operating very high frequency, in old days, we meant this group, like 3-5 based transistors. However, owing to recent advancement in silicon technology, now silicon transistors can be applied to very high frequencies as well. So now the available group is extended for very high frequency applications of today. So out of these many options, currently, as of today, there are 4 most popular options for very high frequency applications. So silicon MOSFET, silicon germanium HBT, and indium phosphide HEMT, and indium phosphide HBT. And based on categories I just mentioned, these 2 devices are silicon transistors, and these indium phosphide HEMT and indium phosphide HBT are 3-5 transistors. Or silicon MOSFET and indium phosphide HEMT is FET, and silicon germanium HBT and indium phosphide HBT is bipolar. So we are lucky to have a very nice option for each combination of these categories. And these 4 devices, I will explain the details. But before moving on to details of each of these transistors, let me provide a general comparison between 3-5 transistors and silicon devices. So advantages of 3.5 devices. Number one, very high electron transport characteristics, or electrons move very fast inside 3.5 transistor. Why? Because high mobility and high ballistic velocities. So it shows very high performance for active devices. And also those 3.5 semiconductors provide substrate with very high resistivity, that's much higher than that of silicon. So it is also good for passive devices as well. And 3.5 devices are good for high breakdown voltage. Why? Because breakdown voltage exponentially increases with band gap. And 3.5 devices like gallium arsenide, indium phosphide, gallium nitride, they have larger band gap than silicon, so they are good for high power applications. On the other hand, silicon devices have their own advantages. Number one, compatibility with baseband or low frequency circuits, which are basically digital circuits. And they benefit from very nicely developed fabrication structure, silicon technology, right? And they show very high reliability, and overall they provide low cost advantages. But when we talk about cost, we need to be very careful, because the mask for lithography is very expensive. So when we make a lot of wafers with a given set of masks, maybe the cost is low. But if we generate only a limited number of wafers or low volume, actually the mask price will be transferred to chip price. So we cannot say low cost. So when we talk about that cost issue, we need to be careful, and it should be explained in terms of wafer volume. Okay, so let me move on to the details of each of those four candidate transistors for high frequency operation. Number one is silicon MOSFET, and I guess you know silicon MOSFET. So there's gate and source and drain, silicon substrate. And in case of NMOS, there is a POL, and there is oxide isolation, and this is energy band along the channel. So this is a very standard device. But for silicon MOSFET, there are other variations as well. So there are silicon MOSFET SOI device. So that is silicon on insulator. First, look at the picture on the left. So this is a SOI device, very similar to MOSFET, traditional MOSFET gate source drain, but there is big difference. There is buried oxide layer just below the channel region. So that improves the device performance. But for this case, some portion of the silicon above this buried oxide is not depleted, only partially depleted, this silicon part, and that is partially depleted SOI. But recently, they developed another type of SOI which has very thin layer of silicon above that buried oxide, and that shows much better performance, and that is called fully depleted SOI, because that silicon portion is fully depleted. Okay? And more recently, there is another type of device, silicon MOSFET. So what about this one on the left-hand side? So it has source and drain and gate kind of partially surrounding that channel region. So compared to traditional MOSFET, in which case the electron flow in the channel is controlled by one direction or from top direction only, this device, the electron flowing through the channel can be controlled from two directions, left-hand and right-hand side. As a result, the performance is improved. And because this channel region is looks like fin of fish, that is called FinFET. And more recently, another version. Now it is similar to FinFET, but this source drain and channel region is divided into smaller fractions so that gate can get around each of these channel regions. So that is called gate all around FET. That is most recent version of silicon MOSFET. Okay? So let's take a look at the evolution of technology node. Technology node is basically the minimum feature size, which is usually the minimum gate length. Like 40 years ago, the minimum gate length was like 1 micrometer, but like 20 years ago, it was like 130 nanometer. 10 years ago, like 22, and now it is 3 nanometer. I'm talking about most advanced technology. So we are talking about 3 nanometer of today. And FinFET first applied at 14 nanometer, and gate-all-around is first applied at 3 nanometer node. Okay, so that is about CMOS. And what about silicon germanium HBT? So that is basically BJT composed of emitter and base and collector. But main difference from traditional silicon BJT is small portion of germanium is added into the base region. So the base is silicon germanium, not silicon. And silicon germanium has lower, smaller band gap compared to silicon. So when you draw energy band gap, it looks like this one. So in silicon germanium base region, the band gap is tapered, and that improves high-speed operation performance. So if you look at the structure, yes, that's a picture of fabricated silicon germanium HBT, which shows emitter and base and collector region. And I'm honored. I participated in developing this particular device when I was in IBM. Okay. Now, what about the HEMT? So HEMT is high electron mobility transistor. So it looks like this one. So basically, it looks similar to silicon MOSFET, composed of gate and source and drain. But the major difference is this channel region and other regions are made of not by silicon, but by some compound semiconductors. And actually, it is composed of stacks of multiple layers with different semiconductors. So if you look at energy band diagram, it looks like this one. So this is channel region, and this is top barrier region. This is bottom buffer region. So channel region is composed of narrow band material, so it is good for carrier confinement. And this is a picture of HEMT. You can see many metal lines, looks like bridges and roads, and this is transistor, and this is cross-section of the gate region. Okay. Now, finally, indium phosphide HBT. So basically, it looks very similar to silicon germanium HBT, but again, the major difference is the semiconductor material that makes up the device. It is based on compound semiconductors, and again, there are stacks of multiple layers with different energy band gap, and that profile of energy band gap can improve the performance of the devices. So this is kind of performance of transistors or for all different types. Well, it shows FT and Fmax. Both of them are kind of parameters that shows operation speed of transistors, and usually Fmax is used to indicate the performance. And in terms of Fmax, now 35 HEMT goes up to 1.5 terahertz, and 35 HBT 1.1 terahertz. And silicon-based technology, silicon CMOS now 450 gigahertz, and silicon germanium HBT like 700 gigahertz. So now we are ready to design circuits operating very high frequencies, well beyond 100 gigahertz. So now I will show some examples of circuits here. Developed from my lab. So for example, this is oscillator circuit operating at 300 gigahertz, and this is a circuit diagram, and this is the photo. So this is the circuit, and those square boxes are the pad for wafer probing, and that is very small. You can see that is well below 1 millimeter, one by one. Another version that is oscillator with even higher frequency, 600 gigahertz. So it has different topology, and it has different layout as well. Not only oscillator, I will show some detectors. And detector detect a very high frequency, and there are two types. Direct detection detect signal at that very high frequency, and heterodyne detection detect after frequency down conversion with mixer and local oscillator. And for example, this is direct detector with silicon germanium HBT circuit and chip photo. And you can see here, this is antenna. Because the frequency is very high, the wavelength is small, so on-chip antenna can be made very small. This is example of 300 GHz detector heterodyne structure. So you can say mixer, local oscillator, amplifier, detector, and antenna. They can all integrate into this silicon wafer. Okay, and finally amplify and another version, 600 GHz detector. Again, it is heterodyne type detector based on mixers, IF amplifiers, and IF detector, and very high frequency detector. So they are all developed in my lab. And another, this is a chip photo of the 600 GHz detector. And this is amplifier developed by NGC. And this is the amplifier having the highest operation frequency, 1 terahertz. So this amplifier operates at 1 terahertz. So now the circuit and even amplifiers can operate this high frequency. So they are the examples of circuit. And let me spend maybe a couple of minutes to show some application example of this very high frequency circuit. Actually, the example is for imaging, terahertz imaging. And we can take image of object with terahertz wave, and that shows very interesting properties compared to conventional images with visible light. For example, we can look inside some object which cannot be seen with visible light outside. So to make the kind of imaging setup, we need to have signal source and signal detector. And the system I'm showing is composed of signal source I showed earlier today, and again, signal detector I showed earlier today, operating both at 600 gigahertz. So this is set up. So there is a source, detector, and there is object, and there are a couple of lenses to guide the terahertz wave or terahertz beam. And this is the picture of the setup. So you can see there is signal source probed here, detector probed here. This is object we have, and there are a couple of lenses to guide terahertz wave. So you may wonder why we use lenses, because that is electronic device, not optical devices. But terahertz wave is so high frequency that it has some properties of optics. So the path of terahertz wave can be guided by those kind of optical lenses as well. Okay? So this is the result. So this is our object. This is chocolate inside paper box. So inside chocolate surface, chocolate and backside, we intentionally attached some metal pieces here, then covered that with a paper box. So from the outside, we cannot see this metallic object. But when we take terahertz imaging, then we can see inside the paper box through the paper. That is one basic property of terahertz. So you can see not only chocolate, but here you can see some metal object here and there. And those pictures can be taken at many different angles. And if you combine those pictures from different angles, basically you can obtain a three-dimensional structure. So that is basically tomography based on terahertz. And yes, after we obtain those 3D structure, you can take a look at the inside of that paper case with this terahertz image from many different directions as you like. So again, this is inside paper box. You can see this kind of 3D structure with carriage imaging, although the chocolate is covered with paper box. Okay, so that was the last slide. And okay, thank you for your attention. Yeah, 20 minutes was too short to show my those work, but I will be happy to take questions after, or the presentation will be made today. Okay, thank you very much.
Thank you very much, Professor Ray, for this wonderful talk. And the last few slides showing the terahertz imaging results are very impressive. I'm sure there will be some questions during the Q&A session. So thank you so much. So now let's welcome Professor Shiben Ko to give us the second talk today. So Professor Shiben Ko, probably many of you already know him because Professor Ko is a Enormous professor at the Indian Institute of Technology in Delhi, and he serves as the chairman of Asia Microwave Products Limited and Hydra Head from 2009 to 2018, and he has been doing a lot of impressive works throughout his professional activities. So let's welcome Professor Ko for this wonderful talk. So yeah, so Professor,
are you able to see my slides?
Yes, we can see it.
You're also able to hear me?
Yes, we can hear you.
Yeah. Good morning. I think we had a wonderful talk by Professor Ray, and I'm going to now discuss about the electromagnetics, which is the most hated subject, but for healthcare applications. I'm a professor at the Indian Institute of Technology in Delhi. Now, just to move this page down. Slide doesn't go down. Yeah. Now, what I put in this slide is healthcare, past, present, future. You know, past means when we were young, we had a simple lifestyle. We had less number of patients, less number of diseases, medical attention was available, physical medical attention, and we had painful diagnostic procedure. For example, biopsies, then mammographies, and non-efficient surgical procedures. And the drug delivery systems were conventional. You take a tablet or you have an injection. But in the present one, everybody is stressful. It's a stressful lifestyle. We have large number of patients. You see the world diabetes data. Now, new medical threats are there. For example, COVID-19, less number of doctors and nursing staff, which was evident when we had COVID-19 pandemic. Painful diagnostic procedures like biopsies, conventional drug delivery systems, and we need quick training of doctors and nursing staff required. And in future, life will be still more stressful. Extremely large number of patients will be there. We won't have enough doctors. We need to learn from the previous medical threats, and then we have to look at non-invasive diagnostic procedures so that, you know, the pain is reduced. Then we have to have targeted drug delivery systems and need to have remote self-medical assistance and also reduction in medical costs. And the enablers will be megahertz to terahertz technology, artificial intelligence, machine learning, cloud computing, smart sensors, 3D printing technologies. So if you look at, we're going to talk from megahertz to terahertz electromagnetic waves. On left-hand side is the frequency here. And on the right-hand side is the wavelength. And I put conventional, which is RF. Then we have microwave band, then millimeter wave band, and sub-millimeter wave band, which is 300 to 1000 gigahertz. On the right-hand side, I've given a lot of applications. They're basically under wireless communication. But recently, there are a lot of interest in medical devices, diagnostics, treatment, and drug delivery systems, which I will cover shortly. Now, why these millimeter wave and sub-millimeter waves have become important? If you look at this is attenuation versus frequency graph, and we notice there are peaks where the attenuation is high, several of the peaks. And then we have very wide bands here where attenuation is low. So because the wavelengths at these frequencies are small, the interaction with particulate matter, water, oxygen, and other molecules is much higher than at very low frequencies. So this is very important for using it for healthcare applications. Now I start with the wearable non-invasive sensor, and you can see I am wearing one of the watches. It uses photodetectors at the back for oxygen sensing. I can get oxygen. During COVID, it was needed. Then there's a crown here to monitor heart rate. Then distance traveled, which can be picked up and which gives us a very important parameter, which is called VO2. What is this VO2 parameter? When we walk, how fast our lungs consume oxygen, and it is very, very important. At my age, I should have 28. Yesterday, I took it, it's 27.6. Still, needs. ECG is perfect, and then blood oxygen. Now, this data is, we use radio frequency links to transmit this data to mobile devices or consoles. So it's very, very important to have this data on day-to-day basis so that we can see whether we are healthy or we need some small tweaking in our exercise schedule to just look at it. So we need RF links even here. Then you see variable-based sensor continuous glucose monitoring. You know, when you eat, glucose goes up. So this is a very nice sensor, which has come from Freestyle Libre. And it's very easy to put. And it has a small micro needle. It goes inside the muscle and picks up from the fluids there and displays continuously your blood sugar. Then you can see I have one fitted into my arm, and using the gadget, I can check what is my blood sugar. So you can read the reading because I had breakfast just now, so it is 165. So it's very, very important that you have 24 hours monitoring of your blood parameters, blood sugar, all those things. And this is again using an RF link between the sensor and the console. Now going further, we can go use millimeter waves for non-invasive glucose monitoring. So this is an example I'm showing you. We can have an incident wave at 60 gigahertz, and then whatever reflection comes back, and we have basically a PTFE substrate on which we have an antenna, disc antenna printed, and then we can touch our fingertip. Nail is 0.5 millimeter. Now the incident signal is incident on this, and the reflected wave basically comes back depending on what's the glucose level into your finger. And this is a 60 gigahertz cavity system. And what happens at different glucose levels? The resonant frequency of this cavity changes, and we can very easily, using the computer scientist, calibrate it and display the results directly onto a console. This device has enormous potential for commercialization. You can put kiosks at the railway station and just touch it, and we get the blood glucose meter. So for students who want to do startups, such kind of products are very, very important. Now, going further from here, we can go to sub-terahertz, as Prof. mentioned, the frequency ranges for sub-terahertz, 100 to 300 gigahertz. So we developed a non-invasive glucose monitoring method. So what it do, basically we can do using reflection measurement. We have an electromagnetic sensor, which is basically a waveguide, and we touch the skin and measure the reflections, and then it goes to a kiosk machine. Inside this, we have a sub-terahertz response. We acquire the data and use artificial intelligence machine learning algorithms, and finally have an output displayed onto the screen. 110 mg per dl is the output glucose concentration. This is the paper which you can refer. Now, this is the reflection measurement, but we can also do transmission. We use two waveguide probes here, and then we put transmission data, reflection data, and do the same thing. So we can again get very accurate readings, and the sensitivity of this method is very, very good, especially in 110 to 170 gigahertz frequency range. Now, let's have a look at the skin. This is your skin, and we have various layers here, and then we have fatty tissues, blood vessels, hair going through. Now, in our study, we used electromagnetic sensor, which was a WR 6.5 waveguide probe, which works from 110 to 170. To mimic this skin, we can use phantom, which is artificially developed phantom, to mimic the skin area between the thumb and index finger. This is called thumb index web space. This is used in our studies. So we use both transmission and reflection of sub-terahertz waves. Now, if you look at here, the sample holder is here, and this basically is skin layer, and then blood inside. And then we have waveguide port 1, waveguide port 2. Of course, we do calibration. And this gives us the scattering matrix, that is transmission and reflection coefficient of the samples. Now, from this data, we can use the algorithms to find out the real part and the imaginary part of the dielectric constant, which is permittivity, as the function of the glucose in the samples. And this can be using the machine learning, artificial intelligence. We can actually display this data on to this. So the second one is basically breast tumor margin assessment. And this is very, very easily done using, again, sub-terahertz EM sensors. If you look at cancer treatment, we have breast cancers are common for females, and we do two types of treatment: mastectomy, which is basically full breast removal, or we can do partial one using lumpectomy. And here it's very important when the surgeon removes the cancerous, okay, there are two important parameters, which is called negative margin and positive margin. If the margins come negative, that means the surgeon has done successfully the surgery and there's no need to do resurgery. But he doesn't know whether the margin is positive or negative. If the margin is positive, then after some time you'll have to do surgery. Typically it takes 14-15 days. It's very, very painful process. So using the sub-terahertz sensor-based thing, we can use again WR65 waveguide probe in 110 to 170 gigahertz to find out these margins, help the surgeon to remove the tumor exactly. So this is what is the setup. We have, if the tumor is in the center, then we have a negative margin and the surgeon removes the entire thing. If the tumor is very close to the edge, typically less than 1 millimeter, we need a very low-cost method, and typical result should be in 20 minutes because we cannot hold the surgery for a long time. So we need to find out how far is this particular portion, and then is there a positive margin. If there's a positive margin, then we go back and ask him to perform the surgery. This can be done while you are in the operation theater. So we developed XY movement automatic, which can basically scan this tumor and find out the scattering parameters. From there, we can construct an image to show whether there is a positive margin or negative margin in the tumor sample. So this is how it is. We have a waveguide WR6.5, then is a waveguide iris. It's basically a very tiny 1.6 millimeter cut here in the flat plate, which acts as a sensor. And then we have tumor and the healthy tissues. We use phantoms using water oil agar to simulate these breast tumors and the normal tissues. And you can see here, this is the XY system, which basically moves this probe over the sample and collects enormous data, which we can use to reconstruct the image for the positive and negative margin. So we do these studies, basically reflection coefficient versus frequency. These are for fibrous, malignant, fibrous, and fat, and we do experiment to verify the simulated results. So these are standard things before we actually proceed with the final measurement setup. This is the final measurement setup here. This is the probe, and this is basically the sample which is picked up from after the surgery. So we have tumor inside and we have tumor at the edge. So this is negative margin and these are positive margin, which we want basically to be mapped. So if you look at, this is how the probe automatically scans the entire slice which is taken and then computes the reflection coefficients, displays it on the network analyzer. And for each movement, we have to put enormous data, and this is sent back to a computer console, and we get the recorded data at various frequencies, various positions, and then we use artificial intelligence neural networks to reconstruct an image. And you can see these are the portions here which the image gives us, that these are positive margins, and the surgeon gets to remove some of the portion from here. And this will save a lot of money and the pain to the patient if we correctly have within less than 15-20 minutes these margins determined. Then we can do ex vivo spectroscopy using imaging of the tissues. Now you have terahertz devices available, as Prof. mentioned. So terahertz time domain spectroscopy can be used to basically, the principle is that most tumors have low absorption than the normal tissue, and therefore terahertz can distinguish tumors from normal tissues. Here you can see an image. This dotted line, this is basically a tumor, and this is no tumor, and we can do the imaging to figure out that which is the tumor region, which is not the tumor region. Without doing a biopsy, we can do that and cut minimal breast or skin so that we leave most of the skin there which is not having malignancy. So terahertz is going to be very, very useful. Terahertz TDS, terahertz imaging. Then very recently, the similar setup which Prof. Roy showed is dental diagnostic and treatment. You have caries in the tooth, and then you can do terahertz imaging to see exactly the depth of these hidden caries. And again, you use these lenses which he mentioned, and then we can use 100 gigahertz source, and then this is your sample, and then take a terasense camera to image these. Now, once we have located these, and we can use microwave and millimeter wave heating, because if it's a lossy dental carie, it basically produces heat when illuminated with millimeter wave signals. And this can be used for automatic sterilization without actually removing the carie. We can do sterilization of this. A lot of research is going on these dental diagnosis treatment. These are non-invasive techniques. Then very important is now millimeter wave therapy, and it has been shown that all living cells generate alternating electromagnetic field. Cell communication in our body is at several frequencies which are falling in the millimeter wave region. And it has been shown that the cause of poor health is unbalance in these waves, and communication with body cells and cell membranes require low intensity exposure at right place using millimeter waves, and this is called millimeter wave therapy. Research has shown healing effects of cardiovascular disease, diabetes. People who have gone through millimeter wave therapy have reduced diabetes problems, wound healing, pain relief, gastric disorders, and also if you have cancer and you go through chemotherapy and subject the part which was cancerous to millimeter wave therapy, the effects are considerably reduced. But it requires millimeter wave sources which are cheaper. Earlier, they used to be tens of thousands of dollars, but today the entire system is less than $1,000. So this is a very, very interesting area. Enormous literature is available. And this is a millimeter wave applicator, which is commercially available from Amazon. And you can see this is the applicator. And depending on why you have problem, is it at tumor or your diabetes, your prostate, your skin ulcer, you can have illumination of, you can contact this probe to the skin at various locations. There is pain, there is hand, you can have it on the palm. So this kind of thing helps in reducing the cancers, tumors, diabetes, prostate. It helps skin ulcers, cardiovascular disease, and also pain management. And this is almost $1,000 is the entire kit which is available commercially today. Now let's look at drug delivery systems. We use either a pill or we use an injection for drug delivery, but newer techniques are coming, which are basically drug patches. These are the drug patches, and this is global transdermal drug sales. But this is useful for low molecular weight drugs. For example, nicotine, painkillers. So you take a Band-Aid, which has a drug, stick it on the skin, it goes inside, and these are very useful. But for treating cancers and other things, we need high molecular weight drugs which don't penetrate the skin. So it is here we use RF energy. So this is the skin. So we have microneedles, and then these microneedles are energized, and there is a drug bank, drug reservoir, and then we illuminate this with the RF energy. It opens the pores in the skins, allows the drug to go, and this is a targeted drug-assisted drug delivery system. Now, these are commercially now available, and Viaderm is a company who manufactures this. This is the applicator, and this is your microneedle with drug reservoir. And this kind of technology is useful for high molecular weight drugs, which are basically hydrophilic drugs, which are cancer drugs, protein and peptide drugs, which are not possible to penetrate the skin. So we use this microneedle array, and this is under this is the microneedle array, and these are the needles. And when we put RF signals here, it opens up the pores here. These are the pores which open up and allows the drugs to go. And this is the radio frequency assisted transdermal drug delivery systems, and such gadgets are available, and there's potential to develop many more gadgets so that you can deliver the drug at the right place. So the next one is minimal invasive screening. Screening is another one where we don't need pain. For example, you have gastric problems, so you have to go through endoscopy. It's a very painful process. But we can have now ingest capsules. It's a capsule which is basically a subsystem which has wireless transmission, sensor, packaging, power sources, data storage, all in a form of an ingest capsule. You swallow it, it can image your entire GI tract and then send these pictures outside so that you can see where is the problem. It also helps us to measure pH, temperature, pressure, motility, gas molecules, enzymes, so that all the parameters in the GI tract can be modified. But on the similar principle, these ingest capsules, which are called pill capsules, several of them are now available, which are drugs. And because nursing staff is now less, doctors are less, and there are old people which have dementia, which have other diseases where they forget. So how do we ensure that they take the pill? So this ingest pill is given, which is a drug, and when it goes inside and it is basically digested in the stomach, it has a transmitter which emits electromagnetic signal, which is picked up by the console and the nursing staff, and it ensures that Professor Call has taken the medicine. So this is very important to use these, and they're commercially now available. So we can actually use electromagnetic signals even to develop several pills which help the nursing staff and less staff in the hospitals to understand that the patient who needs the drugs at proper time is actually taking the drugs at proper time. On the same ground, we have also swallowable capsule. These are called endoscope capsule, which is much more advanced. So we swallow this capsule, and using external transmitter, we can actually move it up and down and we can have imaging system. So if you look at this, the capsule has lights, it has lenses, and then it can send you images till you locate an area which is basically ulcer or some problem. And the capsule nowadays, modern capsules have basically antennas, battery, electronic components, micro reservoirs, micro needles. Then it opens the robotic arms on the wound and delivers the drug. So this is much more convenient compared with the general endoscopy. And many countries have this kind of GI problems, while this capsule will be very useful. It's very cheap, available today. Now you need also several types of antennas because we are doing communication for healthcare application. We can use ultra-wideband antennas. We can use millimeter wave antennas. These are basically monopole antennas. We can use EBG structures to manufacture antennas. Then we can use millimeter wave disc antenna. Again, this is monopole. So we can use multi-layer antennas. And if it's capsule, we can use a wrappable, flexible material and put the antenna on top of it. Very recently, a lot of smart tattoo antennas are used. Tattoos are basically for fashion, but using the tattoo antenna made of metallic inks, you can have a smart tattoo antenna which can receive and transmit the body parameters directly to a console. And this is becoming very modern technology now worldwide. Then we have flexible antennas for healthcare monitoring, also rehabilitation. Suppose, during war or during some riots, where one of the arms gets detached, and so you have only one arm. So we like to rehabilitate the patient. So we can develop a lot of antennas which can be integrated with the textiles. So this is a machine we have at IIT Delhi, where we can actually use the metallic thread to make patch antennas on different types of antennas. Then we can put it on body to study its resonant characteristics. We do it at torso and also free space to see that it doesn't change. Then we can curve these antennas, put it on legs and other things to see that we have minimal change, and whatever change is there, we can record it. And you can see here, we can have it on hand. We move the hand, then we can put it on the leg below, then we can put it on ankle. And in all these cases, a lot of studies have been done. Where is the exact location for these antennas necessary? And we can actually, if we put the antennas on the other shoulder where there's no arm, we can actually use some robotic arm where we can pick up the signals from this arm, and it directs the robotic arm to move in the same direction as we move the arm which is there intact. So these kind of studies are very important if you want to monitor healthcare and also rehabilitate people. Now, we have RF non-invasive lipolysis machine. Most of us are fat, have fat reduction techniques and abdomen, thighs and other things. So what we do, go to a surgeon and he removes this fat. It's very painful, expensive thing, but we have now machines available from Venus Bliss. This is an award-winning machine. It uses multipolar RF and pulse magnetic fields to reduce cellulite around abdomen, buttocks, and thigh. So go to the clinic and give some treatment. Within few weeks and months, your cellulite reduces drastically, and you are non-surgically, basically non-invasively reducing, having your target of reducing the fat around your various organs. Then this is very important in current research. This is RF-assisted hypothermia for enhanced pharmacologic effect at lower dose of chemotherapy. When the cancer is detected, the doctor advises chemotherapy. And when we have chemotherapy, what happens? Hair comes off and it is very bad for the body. People take a lot of time to recover. Now, a new technique which is coming is basically these are nanoparticles, supraparamagnetic iron oxide nanoparticles called Scipions, and this is your chemotherapy drug. So if we give it in low doses, this chemotherapy drug, and combine it with these nanoparticles, then if you look at a typical cancer cell, we have these folate receptors, and when we combine these, we get basically a receptor which is mediated endocytosis. It basically can penetrate this cancer cell. So once it penetrates the cancer cell, the idea is to disperse these nanoparticles into the nucleuses and heat them so that they destroy the cancer cells. And we normally for the studies use a 96 plate where cancer cells and these drugs are put, and then we use RF techniques here. And this work is jointly done. This is my wife and biomedical area. They have perfected this technology. Now you look at the RF system here, which is developed with our assistants. We gave it to biomedical department. We have a metal and insulator thing, and this 96 well plate is put here. And we use a low frequency RF signal, high power, 50 watts, and exposure for 10 minutes. See what happens when there is no nanoparticle, the cells don't die. When there is only SPION nanoparticles, then we have some small effect with concentration of nanoparticles, it small dies. When we have only chemotherapy drug, it still dies. This is the one which shows that it dies. But when we have the Scipions with the drug, basically the cancer cells get killed very fast. And this is a very potential hyperthermia treatment for the cancer cells, and it's proved that the cancer cells totally vanish if you use the nanomagnetic particles and this thing. What the RF helps? It helps in heating the nanoparticles, which releases the drug into the nucleus of the cancer cells. Then we also did some work on developing a multi-channel radar, and this radar basically is portable radar, detects basically your respiration rate and whether your heart is beating. So this has a lot of applications, especially when we have building collapses and people are trapped under the buildings. So we want to find out quickly whether the humans are buried humans are alive. So one of the things we can make this sensor using the technologies Professor pointed out, small ones. So we can fit them on the drones, and whenever there's a building which collapses, we throw these sensors at the building. These are all Doppler radars, and wherever it picks up the respiration is there is heartbeat under the debris, so we can actually rescue these people and save precious lives precious human lives using this technique. Now, ultimately, this is picked up from the last DMI, Professor Bozzi. It's a very interesting slide. This is what we'll be having in future. Wearable sensor-based systems. We'll have psychological biosignals and sensors planted. We'll have thermal signal planted, electrophysiological signals picked up, and then smart textiles, smart watches we are wearing already, but they'll be much more smart. Then thermometers, smart bands, ECG monitoring machines, AMGs, and all the data of yours through wireless communication will be sent to a home care healthcare unit, and this data will go to cloud, and your data will be stored, and you'll have a self-diagnostic computer where you can actually, the doctor can prescribe remote medicines, or you can have self-diagnostics of some of the issues which you are facing as a health. And this, whether you like it or you don't like it, this is what is going to happen. And since we have a lot of undergrad students, so these are the areas which one needs to work on. There's a lot of job opportunities, a lot of startups you can do. Now, in short presentation, you cannot learn everything. So there are 3 books which are Sub-Terahertz Sensing Technology for Biomedical Application, Antenna Architectures for Future Wireless Devices, Wearable Antennas, Body-Centric Communication. They just come in 2021-22. All the details are there. You can make a start by reading some of them and get new ideas and new innovative ideas and develop newer products. Now, the conclusions and recommendations are, whether we like it or not, RF is there everywhere. You cannot escape. So we need to join, all of you need to join MTT Society, whether you're faculty or students, and it will help you learn megahertz to terahertz technology. Like today, you have 3 speakers, which will give you 3 different aspects of these technologies. But we require multiple skills, such as knowledge of basic electromagnetics, which is important. You hate it, but it is needed. Antenna engineering, microelectronics, computer science, artificial intelligence, machine learning, cloud computing, mechanical engineering, material science, biomedical engineering. We need to collaborate with medical science doctors as well as engineering professionals, and together we need to serve humanity. IEEE also wants to serve humanity. There are a lot of programs now, so we can work together and help them have startups to come to us. And future will demand very low cost wearable and wireless devices. And as Professor Rao mentioned, now we have amplifiers, everything available at 1 terahertz. We make use of these things so that we can have better devices, better wearable things, so that we can have non-invasive, basically diagnostic, non-invasive treatments, and make painful journey for the future generations. And with this, I'd like to thank the participants, audience, and later if you have any questions, we can have a discussion. And let me formally thank Prof. Yang and other speakers, and to all of you for your kind attention. Thank you very much.
Thank you very much, Professor Ko, for the very impressive talk, and covers a lot of information about the biomedical applications and also healthcare applications. So very, very impressive. Since we are running out of time, so let's maybe quickly jump into the last talk today. So
Yeah.
if you have any question, let's maybe read out the question in the Q&A session. All right. Thank you so much, Professor Ko, for this very interesting talk. Okay, thank you. Let's welcome Professor Che Xuan, our third speaker today. So Professor Xue is sharing screen. Okay, so Professor Xue is from the University of, the South China University of Technology. So Professor Xue is the current dean of the faculty, and also his background is about microwave engineering and electromagnetics. So let's welcome Professor Xue for this interesting talk regarding microwave technology regarding some magic behind the wireless communications and radar. Let's welcome Professor Xue.
Okay, thank you, Dr. Yang. Can you see my screen?
Yes, we can see it.
Okay, and let's begin. So the title of my talk is Microwave Technology, which is the magic behind wireless communications and the radar. So as to my understanding, DMI, the purpose of DMI is to introduce briefly about the microwave theory and technology to the junior undergraduate student. Hopefully, this talk can attract junior students to choose their future career in microwave. So apparently, Professor Ray and Professor Ko have achieved this purpose, I believe, because they have give very good talk. And here I will give some brief introduction to microwave technology, as introduced by Professor Yang Yang. I'm Xue Quan from South China University of Technology. I belong to.
Professor
Yes,
Xue, sorry,
yes,
would you
yes.
mind turn on the camera, please?
Okay. So I cannot turn on my camera myself. It seems that it was turned
okay.
off by the system.
Okay. Okay, no problem. You can keep going. I will see if I can turn on for you.
So
Okay,
I was saying that I was from the School of Electronics and Information Engineering, and I'm also from the School of Microelectronics of the university. So let's begin. Before I introduce the microwave technology, okay, I would like to introduce the most beautiful 10 equations in the history of human beings, or in the history of human being civilization. We can start from the bottom. The number 10 is the length of circumference of the circle, and the number 9 is Fourier transform, and all the way to the number 1. The number 1 is Maxwell equations, which including 4 equations. So I will tell you why Maxwell's equations ranks number 1 in the most beautiful 10 equations in the history of human being civilization. Maxwell equation is a group of equations representing the coupling relationship between electric field and magnetic field. It's the foundation of classical electromagnetism and the classical optics and electric circuit. So it can be used to analyze and describe the behavior of electromagnetic wave, which is the most important part of electromagnetic wave. Here I show you the spectrum of electromagnetic waves, and you can see the electromagnetic wave can range from very low frequency, which is only a couple of hertz, to very high frequency, which is 30 E hertz. E means 10 power of 21, so from very low frequency to very high frequency. Among this very wide spectrum of electromagnetic wave, microwave is between a couple of 100 megahertz to terahertz. So we call this section of spectrum as microwave, which is one of the most useful frequency bands, especially in wireless communication. In lower band of microwave, we generally call it RF, or radio frequency. And higher band of microwave, we call it millimeter wave or terahertz. And just now, Professor Ray and Professor Stephen Ko have a very intensive introduction to millimeter wave and the terahertz, which are very useful for different applications as well. Okay, so the most popular application of microwave are wireless communications and radar. So these are the two most popular applications of microwaves. For wireless communications, which is very familiar with all the audience here. For example, mobile communication network, wireless LAN, and the satellite communications. So this is the most used for wireless communications. So the wireless communication is use microwave or electromagnetic waves to information transmitting through the waves. The transmitter is modulating the information to EM wave and then transmitting them out to the air. For the receiver, it is used to receive the modulated EM waves and then demodulate them into the transmitted information. So it is information transmission or information delivery through wireless way. Okay, Another application of microwave, most important use of microwave is radar, which is also called radio detection and ranging. For radar, which can be used for fire control radar in the aircraft, and it also land-based long-range warning radar. And currently, most of the cars, vehicles also have radars, which can be help to the drivers to judge the environment of the way. So for the radar, as you can see at the bottom left figure, that there's a transmitter and the receiver of microwave, and the transmitter will emit microwave to the target, and the target will reflect wave to the receiver, and the direction, the location, the speed detection through microwave is operating principle of the radar. There are basically three functions of the radar. The first function is direction, to check the direction of the radar, where the reflection beam is come from, the direction of the reflection beam. The second one is distance, which is used to calculate the speed of microwave and the time between the transmitted and received wave. So we can learn the distance of the radar. And the third function is to detect the speed of the target, because microwave or electromagnetic wave has the effect of Doppler, which means that the frequency shift of the microwave can proportional to the speed of the target. So radar can detect the direction, the distance, and the speed of the target, so which is very useful. Now we have a look at how the microwave technology is evolving. As I mentioned, that Maxwell's equations laid the foundation of microwave technology. So it was proposed or invented in 1950. So from 20th century, the microwave technology was widely used in different applications, and the microwave theory and technology are both developed very fast. As you can see, the first transoceanic radio communication, the first practical radar, satellite communication, phased array radar, and now we are very familiar with the mobile communications. And in the future, terahertz, automotive radar, and wearable devices, which are mentioned by Professor Sven Cole and Professor Ray already in their talks. And you can see this as the futures of microwave. And here I show you a typical wireless system. This wireless system, and actually this system can be divided to three parts. The first part is microwave antenna. The second part is microwave integrated circuit. And the third part is IF and baseband signal processing. So these two parts, the first two parts are microwave related. So I will go down to detail, somewhat down to detail about microwave antennas and the microwave ICs. So these two technology, antennas, ICs, are two enabling technologies for microwave. Because of these two technologies, it will induce some emerging wireless applications. So first, what is antenna? The antenna is a key component of the wireless system. It is used to radiate or receiving electromagnetic waves. It's a port of EM wave going into or out from the microwave circuit. Sometimes we call it transmitter or receiver. So at this side we have transmitter and receiver, and on the other side we have transmitter and receiver as well. And between them we have two antennas. And between the two antennas we have the airs. So what's wireless? Because the antenna can transmit signal from one to another. So without any core or any wires, we can send signal from one point to another point. So here I show some types of antennas. For this one is somewhat like an array of dipoles. So this is a monopole antenna, and here a parabolic antenna. Here this is a Hall antenna. So this looks like the tree, but there are a lot of antenna, and the base station antenna hide inside. So and this is a patch antenna, and this is base station antenna as well, but this is linked baseband antenna, and this is hidden baseband antenna. And here's some antenna in loop. This is antenna is used to indoor antenna for indoor coverage. Okay, so this is types of antenna. Here I show you some state of art of antenna which was designed or invented in our lab. So here is a wide-coupled wideband base station antenna. Here is dual polarization antenna, which use metal surface as radiation elements. Here is filtering dielectric resonator antenna. So this is dielectric resonator as antenna, but it has also another function as filter. And here also some state-of-art antenna which was designed in our lab. Here's metal surface phased array antenna. Here is 5G millimeter wave terminal antenna. This antenna is also a package. Underneath of this antenna, we have millimeter wave transceiver ICs, which was packaged inside this antenna. Here is another antenna, which is 5G wideband base station antenna. So you can see that all the three antenna work in the millimeter wave band from 24 to 30, 45 to 68, and 24 to 30, something like that. Okay, now let's move to the second part, microwave ICs. Before we move to the ICs, we answer a question: what is IC? Actually, IC is electronic circuit integrated on one small piece of semiconductor chip. There are billions of transistors in a fingernail size, which is about 1 centimeter square. Actually, before IC appears, microwave circuits also serves different applications such as communications or radars. At that time, about 20 or 30 or 50 years ago, microwave circuits built up hybrid circuit, which was printed on PCB board, and even sometimes we make use of bulky waveguide as microwave circuit. But now we can make use of IC as microwave circuit, which is very small and very, very powerful function. Okay, here are some applications of ICs in different, for example, in car, in mobile phone, in PCs, cameras, base station, TVs. So as every machines you can see or you can imagine, there are IC inside. So here I show the history of IC, which was also introduced by Professor Ray. In 1947, BGT was invented by 3 outstanding scientists in Bell's lab. And in 1959, the MOSFET was invented. So by BGT transistor and the FET transistors, most popular or most useful component for design ICs. And in 1958, the first IC was invented. Okay, this is the history of IC. And as you can see that in Silicon Valley, Moore's law was said that, and beyond Moore's law. What is Moore's law? Moore's law means that the density of transistor in a chip can be doubled within every 2 years or less. So this is the development of the IC, and we can still see that the density of the IC still growing fast. Even the Moore's law was proposed many years ago. And here is a video shows you how is IC made. This is a very magic or a secret IC, how cents, very cheap cents, can be changed into a invaluable IC chips, because this video is very long. It's a little bit long, so I would like to skip it because we are running out of time. Okay, you can find this similar chip in the internet, so I will not show you this video. But here I would like to show you some state of the art integrated circuit for wireless applications in our laboratory. So here is 5G phased array transceiver, which was designed, proposed in our lab. You can see that in this slide, I see we have four transceivers as 4 corners. It is one, another one, the channel 3 and channel 4, and we have another channel for calibration, and the fifth, the another part of it, we have PAL, up and down converters, and the sources, phase shifters. All the functions are integrated into these 5+1 channel ICs. But the size of the IC is very small, which is only 4.6 millimeter by 3.8 millimeter. Yeah, so this is silicon-based integrated circuit. And here is gallium nitride-based 5G millimeter wave front end. In this front end, we have 3 components. The first one is switch. The second one is power amplifier, and the third one is low loss amplifier. So this is a very high performance front end with very low noise figure and very high power transmission. And here's still another design, which is millimeter wave comb reader transceiver. So ICs and antennas are very basic components in a mobile phone. I will show you here that we have many ICs inside the mobile phone. As you can see that so many IC integrated chips, which are radio frequency or microwave ICs. Beside IC, we have antennas. So these antennas are embedded inside the mobile phone, and there are also some antennas are designed on the frame of the mobile phone. So all these ICs and antennas are use microwave technology. So I can show you here. You will believe in me that microwave is so important in modern society. Okay, so here I will tell you why emerging microwave applications are booming. As introduced by Professor Shiban Ko and Professor Ri, introduced a lot of application of microwave technology. The reason is that the first one is advanced semiconductor process makes the integrated circuit more and more powerful and cheap. And another is that advanced antenna and the antenna array technology also makes a microwave system with low cost, small in size, and very high in performance. So all this is the reason why the microwave application is more and more popular, more and more important in our daily life and in our society. So here I show you some emerging applications, representative applications. The first one is 5G, 6G mobile communication. In 5G, 6G, I will show you some some comparison between 4G and 5G for the latency. 4G is about 10 microsecond. In 5G is less than 1 microsecond. For connection density in 4G only about 100,000 connection per kilo square meter, and for 5G it can go to 1 million. And the data rate is for 4G is only 1 gigabits, and for 5G it can go as high as up to 20 gigahertz, 20 Gbps. So 5G will be the backbone of Internet of Things and Internet of the world. Okay. So the second emerging application I would like to introduce to automotive radar. It can detect speeding detection, colliding volumes, automatic driving. So in the future, I believe the car with microwave radar will be more smart, more safe, and more comfortable in the future. Okay, so these are very short, simple. And the third one is emerging applications about recognition radar. So you can find out what your gesture means. So this is a recognition radar. And the fourth one is medical radar, indoor for indoor location or detection of the breath or heartbeat. Okay, so this is fourth applications. So there will be so many other different very important application of microwaves in the future. So in summary, microwave technology enables emerging wireless applications. For example, 5G, automotive radar, and etc. So, and ICs and antennas are two key microwave technologies. So if you will choose microwave as your future career, and you will have the opportunity to learn how to design microwave ICs and microwave antennas, and your capability will enable to many other, not only 5G or automotive radar, many other important applications in the future. So that's the talk. Okay, thank you for your attention.
Thank you so much, Professor Xue, for this very interesting talk. And his talk was talking about a wide applications from the chip skill to the application skills that including like radar sensing and recognition radar. So thank you so much, Professor Xue, for this wonderful talk. So now we are entering to the question and answer time. So please, if you have any question, please type into the chat window. One of our invited speaker will answer your question here. So, yep.
Sir, good morning, sir.
Yep.
So we have some SKIT, some students wants to ask some questions. Can we do?
Yes. Yes. Can you collect the question and put into the chat window?
Yes, sir.
Yep. Thank you.
So the sensor that we have used in the medical, is it available in the marketplace or we have to make it?
Which one?
So the sensors that we have used are available in the markets or we have to only manufacture that?
No, can you repeat it again?
So the sensors that we have used.
What you have used?
Sensors.
Yeah.
So that we have to manufacture or they are available in the markets?
No, for example, for which application you are talking about?
So medical applications.
No, there are a lot of medical applications. For example, if you want the blood sugar using the sub-terahertz, it's a small waveguide. You can make it in the lab.
Okay, sir.
But for example, for the non-invasive, which I showed you, which is fitted there, they are available in the market. Everybody uses it.
So what is the price range of that?
It depends what kind of sensor you want to use. It's something like 1,000 to 4,000 rupees, which lasts for about 30 days.
Okay.
But if you go to sub-terahertz, then it will be manufacturing cost for the waveguide, which is typically about 10,000 rupees. They're not very expensive.
Okay, sir. Thank you.
Okay, thank you so much. And so let's come to, because there are some questions in the chat window. So let's come to one question from the San Yat-sen University. So the question is asking for the beginners in microwave related fields who want to find interesting and promoting direction faster. So this student want to know how to maintain the sensitivity to the cutting edge field to find a suitable research direction. So this is more about like linking the study to the future cutting edge technologies and find the research direction. So maybe maybe Professor Ray or Professor Shi want to answer this question? So Professor.
Let me try to answer this question. We want to know how to do maintain your sensitivity to cutting edge field and find suitable research directions. Okay, I believe that the first thing you want to be to have cutting sensitivity. You have a very good foundation of mathematics and physics, and then after that you can enter into a specific field of research. For example, microwave ICs antenna is a very good way for you to increase your sensitivity of cutting edge. And after that, if you have a opportunity to go on with your study as a postgraduate student or PhD study, you will have a lot of opportunity to try different ways in, for example, simulations, theoretical analysis, and laboratory experimental jobs. All this job can help you to increase your sensitivity to cutting edge of field and the research stuffs, something like that. Okay.
Okay, thank you so much, Professor Xie. I hope that this answers your question. So now let's come to the next question for Professor Ray. So regarding terahertz applications. So Professor Ray, please help to answer this student's question and to see what do you think about those applications and when it will come to our daily life.
Okay, so thank you for that question. So most of the terahertz research I introduced is in research shape, but some terahertz applications are already applied to real world, especially for science purposes. For example, like some radio telescopes around the world. They use very high frequency beyond 100 gigahertz, maybe up to maybe 600 or 700 gigahertz to detect the signals from the universe. And one example is maybe 2 or 3 years ago, there was a big news about the photo or picture of a black hole. And that black hole image was taken with at the frequency of beyond 200 gigahertz. So I would say there are some real terahertz applications already deployed in real world, but at this point for many scientific applications. And if you are asking when those terahertz applications will appear for our daily lives, I think it will be pretty soon. For example, like Professor Shun Shu already discussed about a 5G or 6G mobile communication system, and for 6G mobile communications, one option is to use frequencies beyond 100 gigahertz, and also for radars, they are working hard to deploy frequencies beyond 100 gigahertz for radars, because the ranging resolution, how accurately you can measure the distance to object, that improves with increased frequency. So currently, the automotive radar, those radars on the cars, they are using about 77 or 79 gigahertz, but they are considering to apply 140 gigahertz radars for many interesting applications, including automobile and medical purposes. So I guess it will be pretty soon when you begin to see terahertz devices and systems around our daily lives. Okay.
Thank you so much, Professor Ray, for this wonderful
Prof. Yang, there are a couple of
discussion.
people on the
Yeah.
chat box asking, are there internship opportunities available? And how do we get them? Yes, there are internship opportunities available. You can write to me in India. I can tell you where you can go and do internship. The second question which they have put here, like, you want to have practical knowledge of these making integrated circuits. Like yesterday, we were in Hyderabad. Sandeep conducted a workshop on hands-on for making microwave integrated circuit using lithography. So such type of workshops will be there, and they could actually go to these places and basically get the details of these. So
Okay.
there are a lot of opportunities available. And there's another question somebody posted on the chat. What is the effect of this ingest capsule on the body? There's nothing as long as you have a biocompatible material which the capsule is coated with, then there is no problem. But there are retractable capsules available where you can take it out or you pass it through your stool. So there's no specific effect right now reported from these things.
Yeah, Professor Shibanko, I think there are two more questions asked earlier regarding the smart tattoo antennas and also the flatness about the skin areas regarding the tattoo antennas. Maybe this is something you can answer.
Yeah, see, basically, if you go through Google search, there are hundreds of them. In fact, there's a lab in Korea. They have developed a lot of tattoo antennas, which basically have sensors and electronics built in. And so these kind of antennas are available. And if you integrate small chips, you can actually transmit the signals to console, and you can pick up a lot of body area parameters. And if somebody is interested in more details, you can email to me. I can send you the literature on these things. And there's another question. Somebody wanted to know how this multi-channel Doppler radar works. I can explain to you offline. You can send me the details. I can send you the paper, and you can go through this.
Okay,
And
thank you.
flatness of skin is not a problem.
Yeah, thank you so much, Professor Shibanko. And I think two more questions here asking about the for the Professor Xie regarding the SpaceX and the Starlink, and also something about the application in E-band. So Professor Xie, do you want to answer those two questions?
Okay, because this is a very good evidence that microwave and millimeter wave are very useful for the future life of our human being. As you already noticed that the SpaceX also launched a lot of satellites, and the connection between the satellite and the Earth must go through the microwave or millimeter wave. So in E-band is a very good band because it's in millimeter wave and it can go through the air. easy. So it's maybe the very useful, because the bandwidth the E-band can provide is also very very large. So it's a very good choice. And we are also planning to develop some E-band microwave chips and antennas for the future microwave for future antenna applications. And I also noticed that somebody asked me, I introduced that antenna in package, whether it's possible for antenna in chip. And my answer is that it is possible, but for microwave and even millimeter wave, it is not so feasible for us to put the antenna in the chips, because the size, the first one size is relatively very large and will make the chip very expensive. The second one is that currently the chip, the wafers we use are still very lossy, which makes the antennas efficiency will be very very low. But in terahertz, it is possible for us to integrate this antenna into the chip, because in terahertz the wavelength is very small, and the antenna size will be very small as well. So the cost of antenna, terahertz antenna on the chip will be acceptable. The second one is because also because the wavelength of the terahertz is very small, so the electromagnetic wave will not penetrate very deep inside the chip, so the losses will be smaller as well. So in terahertz, it is possible to use antenna on chip. Okay, hopefully I answered these two questions.
Thank you so much, Professor Xue, for this answer. There's another question asking about the terahertz frequency range and whether or not that's harmful for human beings. Professor Ray, I think you've been working on terahertz chips and all the way to quite a few hundred gigahertz. Is this, did you consider this kind of a radiation harmless for human beings? Maybe you can comment here.
Okay, so I can answer that question. Okay, so in general, terahertz radiation is a relatively safe frequency band compared to a very high frequency. So the radiation from the chip itself, that can be negligible for human medical effect, and also even for terahertz imaging. Terahertz imaging can be applied to human beings very safely, especially compared to X-ray imaging. You know, X-ray imaging provides much better resolution than terahertz imaging. However, as you know, too much dose of radiation of X-ray is considered harmful, and that's because the photon energy corresponding to the X-ray is quite large. X-ray corresponds to photon energy about 20 or 30 electron volt. And when photon energy is beyond 10 electron volt, that may ionize the molecules of your body. So your molecules in your body may lose electron kind of thing due to the radiation of those photons at X-ray. That's why X-ray is potentially harmful to people when dose is very large. However, terahertz, the corresponding photon energy is only a few milli electron volt. So it is way smaller than the photon energy that affects or that ionize your molecules in the body. So yes, terahertz radiation is relatively safe compared to X-ray, I can say in that way.
Thank you so much, Professor Ray, for this answer. I think people now feel really safe to use terahertz in the near future for the biomedical applications and any wireless devices we might use in the future. We can see that there are quite a few questions about for I think probably for Professor Shiban Ko regarding the skin cancer detection, like the skin depth, and regarding the higher frequencies and also some like effect of the fat reduction, microwave fat reduction. Maybe Professor Shibanko want to comment.
Basically, we're not using, see, we are using RF, which are very low frequency signals. As I said, in some applications, 100 megahertz, which have more depth of penetration. The RF is basically used to open pores in the skin so that the drug can go inside. The other alternative is to use nanoparticles, and we can guide these nanoparticles using some magnetic actuation until it reaches the target, and then we can illuminate it with RF so that nanoparticles become hot, and then they basically release the drug to the cancerous region. So we don't use terahertz directly for this cancer treatment.
Okay, thank you so much. I hope this answers the question here.
And there's one more question. Somebody has put that tattoo antennas, how, if the skin is not uniform, how does it affect? In fact, that is one of the challenging things. When you put a flexible antenna, tattoo antenna is also a flexible antenna. Textile antenna is also a flexible antenna. So one of the challenges is to develop an antenna geometry so that even if you flex it a little bit, it does not change its resonant characteristics. There are techniques people are using for those kind of things. So even if skin is not flat, we can still have a radiator printed on it so that even if you flex the muscles a little bit or the skin you flex, the resonant frequency doesn't change. So it depends on what kind of design you're using. There are available quite a few of designs where the change because of the flexibility of the skin is not that much reflected on the change in the resonant frequency.
Thank you so much, Professor Shibanko. In the chat windows, someone is asking about the radar, like the multi-channel Doppler radar and the far radar.
Yeah, you can basically ask him to send a mail to me. I will send him the papers, which are related to this, so that because it's a very detailed thing, cannot be explained. So we can do that.
Yeah. So for some technical, really technical questions, maybe we can communicate through emails. And yeah. So there are some, I think there are some other questions regarding the summer school and the internship, which Professor Shibanko already answered, but maybe sounds like a lot of interest here regarding those more further training activities, right? So yeah, we do have
in India, a lot of internship opportunities exist, and they can actually send a mail to me. I can tell them what's the procedure to come. We have Indian National Academy of Engineering. They offer fellowships and they can come and work with us. A lot of them. So I can consolidate it and send it to some of the coordinators. They can pass on the information to the students.
Okay, thank you so much. Yeah, I think so. We are now clear that if you're really interested in the internships or any like in-person training opportunities, maybe better to contact Professor Shiban after the seminar. All right.
Sure.
Thank you so much, Professor. There are some other questions, I think, for Professor Ray regarding the in the chat window regarding the distance between the transducer and the chocolate. Chocolate, yeah. So it's very interesting example in the presentation. Maybe Professor Ray can explain further regarding that experiment regarding the terahertz imaging stuff.
Yeah. Okay. So maybe I showed the setup in my presentation, but actually, for my setup, the transmitter, the distance. Okay, distance between transmitter and chocolate was about maybe 20 centimeter or 30 centimeter, that kind of range. So it is definitely far field. And in between that chocolate object and the transmitter, we placed a couple of lenses to guide the terahertz beam and eventually focused on the object. So yes, it is about 20 or 30 centimeter range, and that was far field imaging.
Yeah, so Professor Ray, I think the last question there is asking for the scaling down the transistors. I think it's very technical. Asking for the operation. I think the limit of the upper frequency, right? So this is very, very technical and parasitic delays.
Okay, so I
yeah.
think I can answer that question. I think that's a very good question. So there are a few different physical factors that affect the operation speed of transistors. So number one is kind of transit time, how fast the electrons can travel inside the device from one electrode to another electrode. That's one thing. Second thing is, as you mentioned, there is kind of a delay time due to RC delay. Inside the device, there are many parasitic resistance and parasitic capacitances, and they cause some RC delay. So they are also added to that transition time. So both transit time and those parasitic delays contribute to the speed of device.
Okay, thank you so much, Professor Ray. And I think above there are some questions regarding the radar, especially for the far radar. I think maybe this is for Professor Xue to answer regarding the far radar, far control radar, regarding the applications and yeah, and also yes.
I can answer. I'm not. This is a very good question as well, but I'm afraid that I cannot answer this question in detail. But I can say that for fire radar, it is a very large scale of antenna arrays and the microwave transceiver chips. So without this very large scale of antennas and the transceivers, we cannot have a very precise control of fires. But because this is a military application of microwaves, I'm not working in this area, so I cannot give more details about this radar. I'm sorry.
Thank you so much, Professor Xue. And I think there are some other materials that can be available from the website talking about far radar. Maybe we can have some chat further after the seminar, right? Okay, let's keep moving. So we have around a few more minutes left. I think there are some questions in the chat window regarding the what's the effect of sorry, skip jumping the effect of advanced microwave technology in cosmetic microwave background studies. So this is a question about the effect of advanced microwave technology in cosmetic. I don't know if this question is very special. I think maybe you can send an email to us after the seminar, because it's maybe put more details there asking what is cosmetic, right? Okay, so other question here is about the terahertz generation in a laboratory environment. So maybe this is a question for Professor Ray or Professor Xue regarding terahertz generation in a laboratory.
So actually, I think I can answer the question in previous answer. What is the effect of advanced microwave technology in cosmic microwave background studies? So basically, if I extend that question to general radioscope, radio telescope studies, as I mentioned earlier, as you have sensors operating at higher frequency, actually there is a wider spectrum from the universe that can be detected. So basically, advancement of microwave technology kind of enlarge the spectrum window from which we can study the signals from the universe, including cosmic background studies. So that's one question I can answer. And well, about cost issue, yes, setting up terahertz measurement setup is very expensive, and interestingly, what we are doing in research, terahertz research in the lab is to develop a cheaper version of terahertz devices using the expensive lab setup. Okay, so with the help of that expensive measurement setup, we can develop much cheaper version of terahertz devices that can be used for many different applications, including measurement again.
Thank you so much, Professor Ray. I think Professor Xue, there's a question asking about the automotive radars and its effects on our daily lives. I think Professor Xue,
Okay.
maybe you can.
Okay, I know that the question is raised by the same friends about the fire radar. So it seems that Dr. Sami, okay, I'm not sure whether my pronunciation is correct, is very interested in the radar. So I can say a little bit more about automotive radar, because automotive radar is the basic or enabling technology for the future automotive driving. If we want to drive without human beings' help, so the radar is a must. And you may ask me why we don't use, for example, sonic radar or laser radar. The answer is sonic radar cannot transmit such long, the range of sonic radar is not so is not long enough for the laser, because laser can only operate in clear weathers. For example, if the weather has heavy rains or fogs, and it will out of service. Only meter wave, it has enough precision, and it can work in different weathers. So meter wave is very important, and meter wave is very useful for automotive radars. Okay, even I just mentioned that for the automotive driving, meter wave is a must. Even for the radar aided driver, it's also very useful for us. Now we have some tests using meter wave radar to help the drivers to have more to have safer driving. It's also very helpful.
Thank
Okay,
you. Thank you.
Mm-hmm.
Thank you so much, Professor Xue. I think this answers a question regarding the radars and its potential applications and some other factors. There's a very interesting and important question in the chat window. So what will be the future scope of RF engineer or microwave engineer? I think this is a really good question, and because it will help our students here regarding their future career and their study plan in the next few years. Maybe professors, you can answer this question for this student, and maybe others. I think many other students also have the same question here. So yeah, sorry, the question is about the future scope of
so let me share my version of prospect. And basically, what RF engineers or microwave engineers can contribute to is maybe old days, maybe radar, those kind of things. But now, one very big application for RF and microwave engineers is wireless communication. So as you can see in our daily lives, a lot of communication is transformed from wired communication to wireless communication. So I would say as long as that wireless communication develops, the demand for RF and microwave engineers will increase. And also regarding radar, in old days, radar was applications for mainly military sector, but now they are trying hard to apply radars to our commercial daily lives applications. The starting point was automobile radar, but more and more applications are being found for our daily life. So I would say that the future of microwave and RF engineers are very bright. Yeah.
Okay, thank you so much, Professor Ray, for this simple but easy to understand answer, and hope this helps our students here to clear this question, and hope they all of you can choose microwave engineering for your career. So we are running out of time, so I'm sure there will be many other questions, and which I hope you can keep communications with us and following our program. So there will be more workshops throughout the year in different countries and regions globally. So before we close this session today, I'd like to kindly invite you to open your camera so we can have a online group meeting here. I really appreciate your time today. Thank you so much. Let's take a photo, like a screen card, sorry. Maybe the faculty members in the classroom can take photos from there. All right, I will take a photo here online. Thank you so much.
You can close the screen. There's a presentation thing open still.
Ah, okay. I think, yeah. Yeah.
Hi, Dr. Yang. It seems that I still cannot turn on my camera because it was controlled by.
I don't know. I already assigned you as a co-host. I'm not quite sure why the camera is not working.
Oh, so I'm not the host, right?
Yeah,
You
you're
are
the
co-host.
co-host. No. Yeah, so if I don't know, maybe the camera's disabled somehow. Yeah. Okay, so
Okay, doesn't matter. You move on. You go ahead.
Okay.
Without me. Okay. And I have to go to another meeting. So
Okay.
I leave first. Thank you. And
Thank you so much.
for Dr. Yang for your organization.
Thank you very much.
Thank you so much. Thank you so
While
much.
you can start sharing
Thank
the
you.
presentation, we'll get the full screen for the picture.
Okay. So we are ready here, right? Or we still wait for some classroom? We all good? Okay. Let's
Yang, can you close this presentation, or you are not able to do it?
I don't think I can do it because I think that's Professor Shi's screen.
Okay.
But
you don't have administrative control?
Let me see if I can.
I think you should be able to do it.
Yep. Let me
yeah,
okay.
you can do
Okay.
it now. Yeah.
Okay. Good.
A lot of
yeah. Okay.
Prof, you can also put his video on if he's there, because we're not able to see him.
Somehow I think Professor Shi's camera is not working, but yeah, so we have others video on. Okay, thank you so much. All right, so we are ready. 3, 2, 1, cheers. Thank you so much. I took this screenshot and I will send to everybody.
Okay, and the classrooms, they can individually take and then send it to you.
Yeah, some of the people, they were not having the cam facility in the classroom, so they have sent me the photos. I'll share.
Sure. Thank you.
Thank you so much.
Okay.
Thank you so much, everyone. Thank you, Professor Shibanko. Thank you so much, Professor Ray and Professor Shi. Thank you.
Thank you,
everyone. Thank you.
Thank you so much.
Thank you so much.
Have a good weekend. Thank you. Have a good weekend.